Hello there guys, so I am back again with another tech talk. Today I'm going to talk to you about MPLS, and this is going to be the first in a few MPLS videos. So this one I thought I'd give a quick introduction into what MPLS is. I'll give you a little bit of a hint into some of the packets and what they look like and how we actually structure an MPLS packet. I'll also go over some background, so why we have MPLS, what the history is behind it, and where we can use it. And then in subsequent videos, I'll go over some of the more technical protocol operations. So 102 will be the technical operation or protocol operation of MPLS without any of the fancy protocols that go on top of it, like RSVP or RSVP-TE or LDP. This will be that'll be a bog standard basic MPLS protocol operation talk. And so after that, then I'll probably dig into some of the specific protocols like RSVP and touch on some of the use cases. And then following on from that, I'll probably also go into Isp services that we can facilitate using MPLS. But those are for another day. Today, we will be going over some of the background to MPLS. So let's get started. What is MPLS and why was it invented? So MPLS, the name stands for multi-protocol label switching. And so that was originally invented to overlay ATM and frame relay networks to improve their performance. So you got to remember this was built in a time where we didn't have the likes of Ethernet dominating all of our networks. So this was seen as a way to overlay all of those different networks to make it very simple to provision a link or a path from point A to point B. And so on top of that, you had a level of performance improvement. So we look at, we compare a standard layer 3 lookup to a MPLS, LSP lookup. And we see that the MPLS one is, in theory, less expensive, CPU-wise. So you've got to compare the algorithms that will be running the decisions in those ASICs and in those CPUs of those networking devices. And so if we're doing an L3 or layer 3 or IP lookup, well then we have to do this process of the longest prefix match. You've got 32 bits that you want to match on, and within inside that routing table you may have a /8, you might have a /16 or a 24. And it's really important to make sure that you are selecting the longest prefix match, because that's going to be the most specific route that you want to take. Now that might mean that you have to go through an iteration of 5, 10, 15 different routes that might all match, and you might have to go through a few million that don't, but you have to discount them in some way, and you have to check that they don't match this 32-bit string of value. Now compare that to an MPLS label lookup, and instead we have 20 bits, which is already shorter, so it's less data to work with. And instead of a longest prefix match, here we're doing an exact label match. So we don't want to just say, okay, this is the most specific label. No, this is the exact label. Because in MPLS, we're taking exact actions based on an incoming label or a provisioned label that is matching like a next hop or the path forward for a specific packet, depending on where you are in the MPLS network. What this also means, though, is sure on those on either ends of an MPLS, LSP, or label switch path, you'll have more beefier devices because they have to process more. They have to do both a IP lookup, and then they also have to resolve that to a label. So it means that they have to store a little bit more state. But the benefit of all of this, though, is if you had a 100 node wide backbone, for example, all pieced together with MPLS, those 100 nodes within inside the MPLS domain could be reasonably dumb devices. They don't have to be complex or expensive devices. All they would have to support is some basic protocols, some basic routing protocols, to provide reachability so that you could define those MPLS LSPs. And they would obviously have to support MPLS and any other additional MPLS related technologies that you wanted to support. But the amount of state that they need to store is significantly less than any other device in a normal layer 3 network. All they would have to store is some basic reachability information for the MPLS network, so they could form those LSPs, and then the LSP labels that are defined that are going through that device. So unlike the likes of OSPF, we don't need to store all the state. So jumping ahead one slide to show this diagram for a future discussion, if we take the likes of R2, if we have an LSP spanning from R1 through R2, R4, and then ending on R6, R2 only has to know the details of the label for the MPLS LSP passing through itself. If there was another MPLS LSP passing from R1, R3, R5, and R6, R2 wouldn't be aware of that whatsoever. It wouldn't have to store the state that R3 and R5 need to store, and hence it can reduce its memory utilization. Now, in some devices in wider networks, that memory utilization is a key and critical statistic that people monitor to ensure that you don't hit any hardware limits. So that is another practicality of MPLS. You don't have to store such huge state as you might do in wider IGP topologies. So jumping back into this discussion about what MPLS and where it's used and why it was invented, well, we also see that MPLS is traditionally used in wide backbones. As I mentioned, if you had a 100-node backbone, we could replace a very large portion of those devices with cheaper, less expensive devices and run MPLS over them and get the same reachability and potentially improved performance by using the likes of MPLS. And so traditionally, service providers, big corporations with large wide area networks or backbones will use MPLS to connect all their different locations together to provide an easy way to actually manage that connectivity from location to location. Now, as I've already mentioned, there is a concept of an LSP, and that LSP, or MPLS LSP, is a label-switched path. And so those label-switched paths are the explicit indication of how we route from point A to point B. And so that'll be saying, hop by hop, okay, we want to use this label, and then we want to use this action. So if it sees label 1, we want to punt the traffic out of interface 1 and maybe change the label to label 2, for example. And so that the formation of all of those rules across the network forms what is called a label switched path. It allows you to have this MPLS LSP between point A and point B. Now, they are typically provisioned automatically using the likes of LDP or RSVP. However, you can also configure them manually. And so if you configure them manually, you don't need to worry about things like an IGP running across your MPLS domain. But if you want to use the likes of RSVP and some of its advantages and its extensions, well, then that's where something along the lines of OSPF or ISIS running in your network would be beneficial. It would support your path selection, and it would allow you to make some more dynamic decisions based on maybe some impacts that are going on in your network or traffic patterns that you did not plan for. So, as I mentioned there, typically we'll use something like OSPF or ISIS in our backbone just to provide reachability between those different devices inside the network. That IGP doesn't actually have to store any of the state for your end destination networks. It just has to provide reachability so that we could say on at location A, we need to reach location B. What's the loop back, for example, on that far end device? Yet again, jumping ahead in slides, if we want to form an LSP from R1 to R6, well, R1 and all the devices in the middle need to know the reachability towards R6, i.e. R1 needs to have in its routing table some path or some routing information that dictates the interface and the next hops towards R6. In this case, the routing table doesn't, and most likely we've provisioned the LSP without dynamic protocols, and hence we haven't worried too much about an IGP in this center core. But naturally that means that it is a large admin overhead to manage those labels. Hence, it's typically suggested that we do use something along the lines of an IGP. As I've suggested, MPLS does also support a range of traffic engineering options. So this is something that I mentioned here. We have the likes of RSVP-TE. We have bandwidth to path optimization, and we can have admin groups or path selection. All of that combined together gives a network operator or an administrator or a architect the ability to plan and react to events automatically without needing a large amount of admin overhead to go and change configs on devices or change label states on devices to represent the new topology or the new path based on some kind of impact or device failure. Now, in this fictitious example here, let's say we have gone and statically provisioned this LSP from R1 to R6. If we have, we would have gone into R1, 2, and 4 and set MPLS rules to identify the way in which we're going to forward traffic. So you can see them here, for example. This is a similar kind of rule in human readable language as to what we would configure on R2, and the same here for what we would configure on R4. In this case, if R4 fails, well, this LSP is going to be useless. R2 is going to send traffic to R4, and R4 is going to drop it or not even do anything with it because it's going to be dead or faulty in some sense. So, network engineer wants to change the path to still maintain reachability to R6. Either they've got to go and reconfigure R2 to go via R5, and then they've got to add configuration into R5, or they've also then got to configure R1, 3, and 5 to form a path via this bottom path. As you can imagine, that gets very complicated very quickly the wider your network becomes. This is only a 6-node topology. Now imagine you've got a network which spans countries, continents, and it's hundreds, thousands of devices. That very quickly becomes an admin nightmare. So hence we have these automatic protocols which allow us to programmatically and automatically look at the network and identify state, and in some cases optimize the paths. In some cases select certain paths for certain traffic. So a classic example that you'll see in some Juniper training is the use of like a bronze customer or a standard customer, and a primary customer or a premium customer or a silver or gold customer, for example. And so what that might mean in the terms of path selection is maybe some of these links are more reliable, quicker, more prone to failure, or they just simply have longer latencies. What that might mean for you provisioning services for your customers is a basic customer, a basic subscription customer, might get punted onto any old link, whereas maybe a premium customer has their LSPs specifically pinned or preferenced towards certain groups of links based on link coloring or admin groups, depending on the terminology that you want to use. And what that means is, we can classify this link as a premium link, and this one, all these top paths. And when we dynamically define our MPLS LSP, we can say only go and use premium paths. And so as a result, the MPLS LSP will follow that premium path only. It won't try and form across what would be potentially a standard link. So that's just one potential use case of where we could use some of these traffic engineering options. As I mentioned right at the start, that's a little bit of a teaser for what we can do. There's a lot more that we can do, and I'll hopefully cover them in subsequent videos. Now, one thing that we can also do with MPLS is improve our convergence times. So we can do that through things like fast reroute, bypass LSPs, and node link protections, and in some case, even backup paths. So we can both reactively change our path and fast reroute across the failure. So in the case of R4 failing, for example, R2 can detect that very quickly and spin up a new path or a bypass LSP via R5 towards R6. Yet again, this is utilizing all of that dynamic information that we have just provided to us via the use of an IGP underneath our MPLS topology. We can also use things like backup paths. So we can proactively set up a backup path from R1 to R6, ignoring or not utilizing the existing links in utilization to say, okay, this is my active LSP. I want to form a backup LSP. It's going to go R1, R3, R5, R6. It's not using any of the existing links, so it's all good. Now what we're going to do because of that is if something happens to this first LSP, or this primary LSP, well then we're going to swap over onto a secondary LSP, maybe the bottom path via R3 and R5. Yet again, there's a lot there that you can get into, and there's a lot of options and functionality that you can get into, and it all depends as well on your vendor. Juniper is probably one of the best in class for this, followed by the likes of Cisco and Arista, and I couldn't comment on any of the other vendors or providers, sadly. Now, finally, one of the other classes, and this is a big portion of MPLS utilization, is the Isp Services. So you've got the likes of Layer 3 VPNs, VPLS, multicast VPNs, and inter-provider VPNs. Now what that means is, as you've probably seen on all of these tech YouTubers, it's a VPN, it's a virtual private network. It is the customer's own effectively isolated portion of network across to your own carrier or ISP network. Now what that means is you can then have, in the likes of Layer 3 VPNs, clashing IP addresses. So you can use private IP addresses, a 192.168 address, for example, and that's not going to clash with anything. Even if a different ISP customer uses the same addressing, it's not going to be an issue. The reason why is because we utilize things called VRFs, virtual routing and forwarding instances. And so what they allow us to do is have separate forwarding and routing tables per customer. What that allows us to do is have VRFs per customer to allow us to have separated and isolated routing tables per customer. From that, we can then tag their traffic with a specific label. And that label says, okay, this traffic is for this customer. When you see this traffic, punt it into this customer VRF and handle it in an isolated way. And so that is one of the main technologies that we use MPLS for, actually, is to ensure that we have this separation of customer traffic when we're using and implementing things like VPNs. Yet again, I will cover this in a lot more detail in further videos later down the line. Now, packet format, and this is the last thing that I'll touch on in this video. Traditionally, MPLS is identified and coined as a layer 2.5 protocol, and that is because it sits between both this L2 and L3, or IP headers and Ethernet headers, whatever layer 2 protocol you use. And hence, because we want to use MPLS as a replacement or an overlay to your IP network, we put and sit this MPLS header before the IP header, but obviously after the L2 header. Now, if you remember back to the OSI model video that I did before, you'll know that the layer 2 is the technology that encapsulates the actual physical media that we're using. So that all depends on what physical devices, what physical links and protocols are supported over the physical topology that you have downstream. And the IP header is then that layer 3 lookup and layer 3 information that allows us to do that longest prefix matching, allows us to route traffic over the wider internet. Now, getting into the specifics of this MPLS header, we have a few fields, 4 of them to be precise. And some of them are changed over time. So for example, the traffic class field, that has changed reasonably recently, and it was previously coined as an experimental bit or bits. Now it's officially been labeled as a quality and service and explicit congestion notification field. What that allows us to do in some implementations is allows us to use qualities of QoS and ECN, explicit congestion notification, to change the behavior of traffic on our network via these MPLS LSPs. Now, naturally, I haven't dug into that too much for this video, but it's something that I could potentially cover if you guys are interested. So, of course, we then have the label field, which allows us to, as the name suggests, label this specific packet. And so that's probably the most important field within inside the header. So this label is the thing that is actually doing the heavy lifting here. It is the thing that allows us to identify what rule or what path we should take or what action we should take in our network with this packet. You know, label 1 might say, take this action. Label 2 might say, take this action. And so that's why we use this label to actually identify which action we're going to take. Now, as I've already covered traffic class, and so then we have bottom of stack bit. So that bottom of stack bit allows us to identify that header, this specific header, is the last one in the stack. And so that's useful when we have the ability to stack multiple labels. So as I previously mentioned, when we were talking about use cases, we have the case where we want to provide layer 3 VPNs. So this packet format here right at the bottom is an example of this. So we may have a transit MPLS header. So this header, this MPLS label underneath it, would allow us to traverse our MPLS network. So it'll be saying, okay, send this traffic to here, to here, to here. But then we would have a service or a VPN header to say, okay, this packet is for customer A or customer B or customer C. And so that'll allow you to put the traffic in the right direction on that terminating device. And so that bottom of stack identifier is really important, because if we don't have that, when we process this MPLS header, we don't know whether it is the last label in the stack or not. So by identifying that, we can make sure that when we see that, okay, we want to either take an action or pop it and do a layer 3 lookup. Now this is slightly redundant in the Juniper world, where we have penultimate hop popping. And that allows us to actually pop a label, specifically any one of these, ahead of time, just before we hit the final device in the LSP. So what we'll do when we come to have dynamically or statically defined LSPs is traditionally on this final router before the end of the LSP path. So this is one hop away from the egress of the LSP, so that LSP going from R1 all the way over to R6. We just remove the label. And so the transmission between R4 and R6 is just a standard layer 3 packet. R4 does a standard MPLS lookup. On the ingress from R2 to R4, it sees that the action matching the label that it's receiving is to pop that label. And then it just says next hop is going to be out of that interface, in this case, port 3. We send it towards R6, and happy days, it gets there. And R6 now is just reviewing that as a layer 3 packet rather than an MPLS packet. So that can save us a little bit of processing time on that final egress device. So that is that penultimate hop popping, and it's kind of supported, kind of replacing the bottom of stack bit in these fields. And then finally we have this time to live field, which is 8 bits, and that, very similar to the IP header, allows us to ensure that we don't end up in some form of MPLS LSP loop. The worst thing that we can have in our network is a loop of traffic constantly building up and then ending up causing a storm of packets. Hence, we use the concept of that time to live. So if you've seen my other videos on the IP headers, I can't remember exactly which video that is, but so when I covered that, you have that concept of time to live with inside the IP header. And so this time to live here is actually populated from the IP header when you encapsulate the packet into an MPLS packet. And so it just allows you to inherit what the original time to live, or TTL, was, and then extend that over your MPLS domain, thereby making sure that you actually don't exceed the TTL and it ensures that you actually have a reliable transfer through your network and you don't end up causing storms, like broadcast storms, or just endless loops of traffic that never exit or never die out in your network. So that was a bit of an introduction into MPLS, some background as you would into what MPLS is, why we use it, and where it can be used, and some of the tiny little bits of detail to formulate the packet structure. Hopefully that was useful, and please look out for the next video in the series on a bit of a technical introduction onto the protocol operation of MPLS.